Hello again, everybody. In this second video on Unit 5, we will wrap up what you have already studied about oxidative addition reactions. Oxidative addition and its reverse, reductive elimination, both reactions play a central role in catalysis. The oxidative addition of a substrate AB to a complex results in the cleavage of the bond between A and B to form two new bonds, metal A and metal B, A and B becoming X-ligands in the metal coordination sphere. We can also see it from a different point of view, in which the metal inserts between A and B. We can also say that a neutral substrate adds to a metal center and in doing so oxidizes the metal, typically by 2 electrons. The transferring of the 2 electrons from the metal to the incoming substrate AB breaks the bond AB, thus forming 2 new anionic ligands. At least one of these new anionic ligands ends up bonded to the metal center. In these kind of reactions, a coordinatively unsaturated complex with the metal in a relatively low oxidation state undergoes a formal oxidation of 2 electrons, while its coordination number increases in 2 units. Therefore, the number of valence electrons also increases in 2 units. The complex undergoing the oxidative addition must have vacant coordination sites, that is, at most 16 valence electrons, because the resulting complex must not bear more than 18 valence electrons on the metal. At least 2 non-bonding electrons, because they will be required in order to form the 2 bonds with A and B, which will become 1 electron donor ligands, such as X anionic. A low oxidation state, since this oxidation state must increase by 2 units in the reaction. Therefore, take always into account that oxidative addition cannot occur in D0 complexes that do not have available electrons in their valence shell. The complex also must have a coordination number at most equal to 4. The square planar complexes are ideal because they form octahedral complexes upon oxidative addition, and the coordination number increases in 2. Finally, these reactions are favored when L, the ancillary ligands, are strong donors. The mechanism of these reactions varies and depends on the polarity of the AB bond and the nature of the complex. These are 3 main classes of molecules or substrates that can perform oxidative additions to metal centers. Non-electrophilic apolar or slightly polar non-reactive substrates such as dihydrogen, dioxygen, disulfur, alkanes, and trimethylsilanes, and so on. Electrophilic often reactive substrates such as alkyl or aryl halides or hydracids. Non-electrophilic intact with a double or triple bond such as alkenes, alkynes, and dioxygen. Well, non-electrophilic AB apolar or slightly polar non-reactive substrates do not contain electronegative atoms and or are not good oxidizing agents. Aside from dihydrogen, they are often considered to be non-reactive substrates. These molecules generally require the presence of an empty orbital on the metal center in order for them to pre-coordinate prior to being activated for the oxidative addition reaction, like here. We are talking about hydrogen-hydrogen bonds, hydrogen-carbon bonds, silicon hydrogen bonds, silicon sulfur hydrogen bonds, carbon-carbon bonds, etc. Dihydrogen is by far the most important for catalytic applications. We can talk then about a concerted three-center mechanism such as that in the Vasquez complex, 16-electron complex with dihydrogen. A sigma intermediate complex or transition state is believed to first form, then electronic transfer from the d metal orbital into the antibonding sigma orbital of the dihydrogen provokes the cleavage of the hydrogen-hydrogen bond in the more rapid second step. It is important to point out that in the presence of electron withdrawing ligands or a positive charge on the metal, this intermediate state complex with the dihydrogen is favored. These kind of ligands prevent the oxidation of the metal. In this case, that would be from 1 to 3. Vasquez complex gives many oxidative additions through this mechanism. However, it does not give oxidative addition with alkanes due to the very high dissociation energy of the carbon-hydrogen bond. In order to carry out this oxidative addition of alkanes, it is necessary to start from a high-energy 16-electron species, such as this one, which has been photochemically generated from an electron-rich complex, that one, containing a CP star or pentamethyl cyclopentadienyl ligand. The SN2 mechanism applies to strong polar substrates such as alkyl and aryl halides and hydrazides and presents all the characteristics of the organic SN2 mechanism. These molecules do contain electronegative atoms and are good oxidizing agents. They are often considered to be reactive substrates. These molecules do not require the presence of an empty orbital on the metal center in order to perform the oxidative addition reaction. That is, 16 or 18 electron complexes are okay. An example of the oxidation addition is shown in this slide. Note that the starting metal complex in this case is a 16 electron. The methyl bromine bond is broken on the oxidative addition reaction, generating two new anionic ligands, the methyl and the bromide ligands. If the starting metal complex is 16 electron, as in this case, both ligands will usually end up coordinated to the metal to make an 18 electron complex. On the other hand, in the case of a starting 18 electron complex, as this one, only one of the two anionic ligands, usually the strongest binding, generated from the oxidative addition, will end up coordinated to the metal unless a separate substitution reaction occurs. In this case, the alkyl anion is the best donor ligand and easily beats out the more electronegative and poorly donating chlorido anion. Note that the eta-1 allyl ligand can convert to the generally more stable eta-3 allele upon carbonyl ligand dissociation. Complexes with two or more adjacent metal atoms can also participate in oxidative addition and reductive elimination reactions. This often involves both metal centers. If so, then each metal changes its oxidation state by only one instead of two. This also often involves the making or breaking of a metal-metal bond. Finally, non-electrophilic intact molecules may or may not contain electronegative atoms, but they do need to have a double or triple bond present. A metal center with an empty orbital is needed, that is, 16 electron or lower number of electrons, in order to pre-coordinate the ligand before the oxidative addition occurs. Unlike most of the other substrate molecules that break a single bond and form two separate anionic ligands upon the oxidative addition, these ligands have double or triple bonds, and only one of the pi bonds is broken, leaving the sigma bond intact. The ligand thus picks up two electrons from the metal and becomes a dianionic ligand. Typical intact ligands that can perform an oxidation addition without fragmenting apart are alkenes, alkynes, and also dioxygen that, remember, can also act as an electrophilic substrate. One often needs to have electron withdrawing functional groups on the alkenes or alkynes in order to help promote the transfer of electrons from the metal to the ligand. In our next video, we'll work on the opposite reaction, reductive elimination. Thank you very much for your attention.